Hi, I'm HANIF bin Sulaiman. Today, I'm gonna explain to you about the topic of Chapter 3 Physics Form 4, which is force and pressure. Okay, subtopic number 1, understanding pressure. Pressure is defined as force acting per unit area, which is pressure P equal to force F over area A. The unit of pressure is Newton meter square or Pascal. Okay, for example, here, an elephant weighing 40,000 Newton standing on area of 0.1 meter square exert 40,000 over 0.1 equal to 400 kilopascal pressure on the ground. Application of high pressure, for example, like scissor, high pressure to enable a scissor to cut easily. Next, ice skate, high pressure melt ice enabling skater to move easily. Running shoe, spike on the base shoe exert high pressure to increase grip on the ground. Okay. Next, application of low pressure, example like large wheel of tank, low pressure on the ground so that tank will not sink. Large feet or camel, exert low pressure on sand so that camel will not sink into the sand. Okay. Next, like snowshoe, prevent Eskimo from sinking into the snow. Next, subtopic number 2, understanding pressure in liquid. Okay, pressure in liquid. An object immersed in a liquid experiences pressure due to the weight of the liquid acting on it. Pressure in a liquid act equally in all directions. Okay, example, water in a tin. When have a hole in the tin, they will perform water jet out from the water from the tin. Okay. Pressure in liquid and depth. Pressure in liquid increase with depth. As you can see, when the depth is increased, the pressure also increase. So that the pressure go further than the upper hole. Okay, next. The stronger jet water is same like this. Okay. As I said earlier, the deeper the hole, the higher the pressure. Same like here. Bubble in carbonate increase in volume as it rises to the top as pressure increase with depth. Same like this. Pressure in liquid and density. At the same depth, pressure exerted by a denser liquid is greater than pressure exerted by the less denser liquid. Like we can see here, water, the density of 1000 cooking oil, only density of 800. Okay. Then we can see the distance of water jet from can is far, but for the cooking oil that is more lesser density is near to the can. Okay. Okay, pressure in liquid. Pressure in liquid have a new formula which is P equal to H rho G, as we can get from normal formula. This is pressure equal to weight of liquid over area, mg over A. M is changed to rho V, then V change into AH. Then we cut the H, we can get H rho G. Okay, rho is liquid density. Application of pressure in liquid, typical hydroelectric dam using as whole water to store and generate electricity. The base of a dam is thicker than the upper part to withstand the higher water pressure at the base of the dam as pressure in water increase with depth. You can see here is more thicker than upper because more pressure on the bottom. Next, water tank. Application of pressure in liquid like water tank. Water tank in a house is placed below the roof. Water pressure force water to flow out the tag. Okay. Water flowing out from the Q on the first floor is stronger than the water out from the P on the third floor. Why? Because the distance of the tag Q on the first floor from the surface of water in the tank is more bigger than P. Okay. Okay, for simple example, the figure shows glass tube filled with 50 cm height of liquid M and 30 cm height of the liquid N. The density of liquid N and M are 10,000 and 2,050 to 2,500,000 respectively by giving G equal to 10. What is the pressure of M at X and B, liquid M and N at Y? Okay, for X, for A, you can see, we take rho for M, rho G, we put H, because only X, take this, we get 5 kilopascal. But for B, we take both. We do same like this one and get 5, but we add another more, which is the bottom one. Then we can get 12.5 kilopascal. Subtopic number 3, understanding gas pressure and atmospheric pressure. Okay, gas pressure. A gas molecule are constantly in motion. This molecule collide with each other and with the wall of the container containing the gas. A pressure, gas pressure, is exerted by the molecule of the gas colliding with the slide of the container. The more energy a gas has, the more energy its molecule will have, and the more pressure will therefore be exerted. If there is more gas inside the given container, there will be a higher number of average collision with the side of the container, and more pressure will therefore be exerted. Okay, for atmospheric pressure, our Earth is surrounded by a thick layer of air. The air molecules are constantly on the move. All objects will experience a pressure called atmospheric pressure due to these all molecules colliding with them. The magnitude of Earth's atmospheric pressure is 0.1 times 10 to the power of 5 Newton meter negative 2 at sea level. Atmospheric pressure decreases with high above sea level as the density of air decreases. This causes air molecules colliding with object. Okay. Existence of atmospheric pressure. If we want to know, a metal can with water, we heat up, then we seal the can after we heat, then we put the metal with cool water, so we can see the can will go down inside. That show the atmospheric pressure push the can. Okay, the metal is crushed because the atmospheric pressure is greater than the air pressure inside the metal can. Okay, application of atmospheric pressure like rubber sucking for hanging object, drinking straw, siphon. Okay, first, rubber sucker for hanging object. Okay, when the sucker is pressed into the place, the air inside is forced out. As a result, the pressure inside sucker become very low. The sucker it then held its position, the high atmospheric pressure on the outside surface. Okay, the atmospheric pressure push outside the surface of the sucker. Next, drinking straw. The higher atmospheric pressure forces the liquid to flow up the straw into the mouth, because the pressure inside here will be lower because we suck the air. So the atmospheric pressure will force it to go into the straw. Okay, for siphon, first we have the rubber tube. And second, pressure of the surface of water is equal to atmospheric pressure. Then the water will go out at point A. The pressure is equal to the atmospheric pressure to at here, but pressure at B is more, so we need to add rho GH here in this. So pressure at B point is greater than atmospheric pressure. As a result, the water flow out from the rubber tube. Instrument used like Bourdon gauge for atmospheric pressure, mercury barometer, aneroid barometer or floating barometer. Okay, sample example. Apparatus set up with use measure atmospheric pressure. Okay, this is barometer, mercury barometer. You can see, calculate the pressure at point Q in PA unit. Okay, we give in mercury density. Solution. We find the H first. So adding 7.5 with 515 from here to here, only the mercury. And then we get high. So we use the formula rho. This is G, this is H. Then we get 122.4 kilopascal. Next, applying Pascal principle. Okay. Pascal principle state that pressure applied to an enclosed fluid is transmitted equal to every part of the fluid as well as to the wall of the container. Okay, when the piston is pushed in, water will shoot out of the hole in the flask in all directions and with equal speed. Okay, this shows that pressure in water is transferred uniformly through the water. Okay, application of Pascal principle like hydraulic jack. A hydraulic system apply Pascal principle is working mechanism. It can be used as a force multiplier. This hydraulic system, a small force F1 is applied to the small piston X, result in a large force at F2, the large piston Y. The pressure due to the force F1 is transmitted by the liquid to the larger piston. Okay, this is the formula for Pascal principle. Okay, this is an example. You can see, push. Okay, application of Pascal principle like hydraulic system in car brake. Okay, when we push, small force is directed into the brake pedal. The pressure produced will be transmitted to the brake fluid to the car tires. This produces a large force on the brake pedal which slow down the rotation of the wheel. Okay, you can see. Okay, for example, the figure shows a hydraulic jack cross-sectional area of small piston and larger piston 0.4 and 8 respectively. If the smaller piston is pushed with 0.820 Newton, what will be the force experienced by the large piston? Okay. We use the formula given. We take out the information given, like 20 is the F1 and 0.4 is the A1 and 8 is the A2. Then we use the formula given. Then we put in the information to the formula, and then when calculate we can get 400 Newton. Okay, next for applying Archimedes principle, buoyant force. Archimedes discovered that an object is partially or fully immersed in a fluid experience an upward force on it. This force is known as buoyant force. This buoyant force is caused by the higher fluid pressure acting on the base of an object compared to the fluid pressure acting on the top surface. Okay, this is some of the example. You can see a piece of cork pushed below the surface of the water and released will immediately rise to the surface. The cork is buoyant because the cork is acted by buoyant force. A sheet made of iron can float on the surface of the sea due to the buoyant force F, which is balanced by its weight mg. Okay, for a bubble release rise to the sea surface due to the buoyant force acting on them too. A hot air balloon rises from the surface of the earth due to buoyant force acting on it. Next, buoyant force and weight of liquid displays Archimedes principle. Okay, loss in weight of the stone equal to buoyant force and equal to weight of the water displaced. Okay, this is the formula for Archimedes principle. Very simple. You can see here. Archimedes principle state that the buoyant force on a submerged object is equal to the weight of the fluid that is displaced by the object. Okay, application for the ship. Okay, a ship float because it displaces seawater with a weight equal to its own weight. When more load are put into the ship will sink further. Okay, the ship will sink when the ship is overloaded. To prevent the ship from sinking, a plimsoll line, which is this one, is marked on the hull of all ships to show the limit which are safe for the ship. Okay, this next application for Archimedes principles is submarine. When submarine have two tanks, when the tank inside is empty, it want to stay float on the sea surface. Okay, but to stay stationary below the surface of the sea, the blast tank is partially filled with water, and the buoyant force is equal to the weight of the submarine. But if to sink into the sea more, water is pumped into the ballast tank. So at this, buoyant force is lower than the weight of the submarine, so it will go further deep into the sea. Next, simple example: an object of density of 40 and mass of 500 gram is immersed in a liquid of density 2 gcm-3. Calculate the volume of liquid displaced. To calculate the volume, get the m is the mass, divided by the p, rho is 40, and get 12.5 cm squared. For B, the mass of the liquid displaced. Okay, to find, let the liquid mass as m and density as p. So m naught is p naught times volume. So p naught, you know, as 2 rho naught, sorry, and then volume 12.5. If we get here, then we can get the m naught, 25 gram. Then for the C, the buoyant force is experienced by the object given G equal to 10. Then we use the formula given here, m naught times G. M, transfer it to kg, 0.025 times 10 equal to 0.25 Newton. Next, for last subtopic, understanding Bernoulli principle. Bernoulli principle states that the pressure of a liquid decreases as the velocity of the flow of the fluid increases, and vice versa. Okay, pressure of the fluid decreases, the velocity of the fluid increases. Okay, a sheet of paper is held in horizontal plane in front of the lid. Air is blown across the top of the paper. The free end of the paper is seen to rise. The flow of air at the high speed creates a region of low pressure across the top of the paper. Here, the still air beneath the paper is at higher pressure, and net upward force lifts the paper. This is a diagram show that the cross section of the wing of an aeroplane. Okay. The shape is called aerofoil. The shape of the wing causes the air to flow faster over the top of the wing compared to the lower part of the wing. Hence, the region of high pressure exists below the wing. This difference of pressure causes the resultant force to act at the wing in an upward direction. This force is called lift. Okay. Lift enables an aeroplane to ascend. Okay, next, application of insecticide spray. When the piston is pushed, air flows out from the nozzle at very high speed. According to Bernoulli principle, a region of low pressure is created at the nozzle. Here, the high atmospheric pressure then push the insert pressure liquid here up through the narrow tube toward the nozzle. Then the liquid insecticide mixed with the air is then ejected and spray of fine droplet insecticide. Last with for exercise. Fill in the blank. Okay, figures below show and what? The upper region of the aerofoil has higher air velocity and the lower region of the aerofoil. Okay, what is this? This is aerofoil. Figure show an aerofoil. Okay. By Bernoulli principle, the lower region has what? Pressure, and then the upper region of the aerofoil. So the lower region have higher pressure. This causes a lifting force on the aerofoil. Okay. Okay, the end. Thank you for watching. That's all for me.